Welcome back, grade 10s. We are now nearing the end of measurement. I hope you are enjoying or have enjoyed the videos I've uploaded on Classroom for you. And the diversion of videos is just to get a better understanding of concepts. When it's explained in different ways, you tend to look at it differently and perhaps and hopefully get a better understanding. So to this point, we have covered surface area and volume of prisms, which was the revision of grade 9. And then grade 10 work included pyramids, spheres, hemispheres, and cones. So you have all the notes for those concepts. You have videos explaining how to calculate surface area and volume for all of the three-dimensional shapes mentioned. Today, I am going to focus on the application questions, and I will do 2 examples now, just to give you a little bit of an insight on how to use the formulae. Now remember, the formulae is normally given to you and in your question paper, excuse me, or on a data sheet. So the first question I'm going to go over is this one. As I said, the focus today is on application. How do you apply all of the theory to a word problem, basically? So let's look at example 1. The diagram below represents the Northgate Dome, which is in the shape of a hemisphere. And if you go to your notes, I've given you formula sheets describing hollow and solid hemispheres, and the formulas there for you. The diameter of the circular floor of the dome is 100 meters and the height is 50 meters, as indicated here. The manager decides to paint the floor and exterior surface of the dome with a waterproof coating. So you've got to think about, what does that mean? Calculate the volume of the dome, nearest whole number. Okay, so in order to find the volume of the dome, we need to think about the hemisphere, the volume. And that's important, rounding off to the nearest whole number as per the instruction. Okay, so let's look at this question. Where do we start? We will start by writing down the formulae. So A, when you're dealing with a solid hemisphere, the volume, whether it's a hollow or solid hemisphere, the volume is not affected because it's still holding the same capacity. However, when you deal with surface area, then there's a difference in the formula. So now let's focus on the volume. You can go back to the lesson on hemispheres, spheres, and cones, and you can refer to the notes and all the formulae there if you have forgotten. So if you go think about it, it is 4 over 6, which is 2 over 3. So it's 2 over 3 pi r cubed. So that's the formulae for volume of a hemisphere. Now, let's see, what do we have here? We have the diameter of 100. We need radius. So therefore, radius would be 50 meters. Now, all you do is plug these values into the formula, and that leaves you with 2 over 3 pi r is 50 cubed. And that, if you put them together, that would be 250,000 pi divided by 3. And then you take your calculator, and remember you need to include pi in this answer. So it will be 250,000 pi, the pi appears on the calculator, equals divided by 3, and that gives you 261,799 meters cubed. That's volume. Okay, that's A. Straightforward question. B. What is B asking? B is asking cost of the amount of waterproof coating if coating costs 10 Rand per square meter. Okay, so before we get to the cost, we need to know how much paint we need. So what is it asking? It's basically asking, you're not going to paint the inside. They're talking about exterior surface, which means it's the outside. So it's the surface area of the solid. So B is asking for the surface area of this solid. In this case, it is the hemisphere. So how do we work it out? Let's see. What is the formula for surface area of a solid hemisphere? So if you think about it, you've got to do the curved surface and you've got to include the circle at the bottom. So it would be surface area, the formula is simply 3 pi r squared. Again, refer to the sheet that I've uploaded on Google Classroom for you, and you will see the difference in all the formulae. And now you simply plonk in the radius, which is 50 squared, and that is equal to 7,500. That is pi, and then in the next step you will include pi and round it off to 23562, and remember it's surface area, so you're dealing with meter squared. Now that does not answer the question. They want to know the cost. So 1 square meter costs 10 Rand. Hence the cost would be is equal to, so it's 10 Rand times that 23562 meters squared, and that is equal to it's in costs, so you've got to represent it in Rand, so it's 235,620. That is how much it will cost to paint that section of the dome. Okay, so that's example 1. This wasn't too difficult. Now let's go to another example. Okay, so this question brings in a lot of content. So let's start looking at this. The diagram below represents a swimming pool that a company wants to build. All answers must be correct to 2 decimals. Okay? Again, it's quite important to take note of the instructions. Question 1. Calculate the swimming pool's capacity. There's a new word. And then the total area of the inside of the pool, walls included. Right, where would I start with this question? Now let's look at it. What is the difference between capacity and what is the difference between capacity and volume? Now basically, some of you may say it's the same thing, but there is a technical difference. Volume is the amount of space taken up by an object. Capacity is the amount a container can hold. And when the question is asking capacity, there is something very important that you have to remember, and I'll talk about that at the end of the solution for A. Okay, so just remember capacity. Give me examples of capacity. If you're talking about capacity, you're talking about the amount of water a cup can hold, for example, or maybe the amount, how many people can fit into a room. That is capacity. Volume, the unit of volume is always cubic units, and then every other unit of measurement would fall with capacity. Now it's important to understand the formulae. And as we know, the formula for volume is described as the area of its base multiplied by the height that base is extended by. Quite important. And that simply means the shapes on either side of the height have to be congruent, identical. Now, when you are working out volume or capacity, so we're going to treat this as volume for now. We'll highlight the capacity part at the end. So you can think about volume. How would you work out volume? That's exactly how you would work out capacity. Now there is a shape and it's a swimming pool. You can see, so this is here a trapezium. So let's give it some labels. So let's call that A, B, it'll be easier to work with, C and D. So I'm going to start with A, B, C and D. Let's look at it. So in order to find the volume or the capacity of the pool, so how much water can this pool actually hold? Now remember, it's slightly skewed. So if you're thinking about a pool, it's not a flat surface. It's not flat, so it's elevated slightly at the top there. So the dimensions of the height there, as you can see, the 1.6. So A, B, and C, D are not of the same length. That's the first thing you need to recall. So when you're working out the capacity here, you need to consider that this section is a higher wall than that section. So you can't actually worry about that. If you pour water according to that, it's going to leak over or spill over. So please take into consideration. So where would I start? How would I find the area of the base? What is the base? How do you identify the base? Because volume is area of the base of the shape times the height by which it's extended. So let's look at it. Look for congruent shapes or look for identical shapes. So that's the first one. So let's write it over here. So look for, remember that symbol represents congruency. Congruent means identical. So let's label this here. So this would be E. We'll call this section F, G, and H. Okay. So ABEF is a rectangle. CDHG is a rectangle. But are they identical? No. Although they share the same width of 16, their lengths here are different. This has 2 and that's 1,6. So you cannot say that this is projected by, this cannot be the height because these two rectangles are not congruent. Hence, if you look, you've got a flat base there, a rectangle, but there's nothing at the top because it's a swimming pool. So that falls away. So the only other section left is the side wall here. And this side wall, ABCD, is a trapezium. Okay? EFHG is the trapezium on the opposite end. Hence, they are congruent. So the congruent shapes here are the trapeziums. And because the trapezium is the congruent shapes, or the trapeziums are the congruent shapes, this has to be the height. So the height will be represented as the distance between the two congruent shapes simply. Because this trapezium is extended by that height to get another trapezium on that side. Okay. So you're looking for congruent shapes, and in this case it is the trapezium. So which means, therefore, the base of this swimming pool is the trapezium and not the rectangle. Please remember that. A lot of learners will think the base is always on what the shape is sitting. It's always at the bottom. No, that is not true. So as you can see, maths is exciting. You learn new things for every question. That's what makes it exciting. Now, let's look at this. I need to work out the area of the trapezium. Now you can, if you do not know the formula for the trapezium, you can actually divide this into a rectangle and a triangle. So I'm just going to construct the perpendicular height here going down. So there's your perpendicular height. Let's put a little right angle triangle here. So that's the height of this face. It's not the height of the entire pool, it's the height of that face. Right, so let's start by finding the area of the trapezium. So area of trapezium is the formula area of trapezium, and I'm going to put the labels A, B, C, D is equal to, remember trapezium is, so this is the parallel side and that's the parallel side for a trapezium. So it's half the sum of the parallel sides, which is AB plus CD times the height, which is this one here. So I'm just going to put height there, H. The height is the distance between the two parallel sides. Or as I said, you could work out the area of this triangle, that rectangle, and then you can add them together and that will give you the area of this trapezium, which is the base of the shape. And we need the base of the shape, the area of the base, to find the volume or the capacity. So before I use this formula, I need to find out what this value is. The unit for the height, it's not given. All that's given is this is 1,6. So if you look at this, CD will be 2 because it runs with that rectangle. So this section here, this little section here, let's put a little highlighter there. That little section there would be 0,4. It will be 2 minus, so let's call this T. Okay, so CT is equal to 2 meters minus 1,6 meters, and that is equal to 0,4 meters. So that little section is 0,4 meters. Now, if you think about it, there is your right-angled triangle. This measurement, AC, we already know that AC is 25 meters. AC is equal to EG, so that is 25 meters. So therefore, we have a little triangle going on here, ACT. I've given it labeled so it's easier to explain. So in triangle ACT, we can use the theorem of Pythagoras to calculate the length of AT. So you have 25 squared, so you're finding that is the hypotenuse side would be AC. So therefore, AT squared is equal to 25 squared minus 0,4 squared. And the reason is Pythag, and that gives you 624,84. Therefore, AT is equal to the square root of that, which is equal to 24,996 meters. Okay, so that's my height, H, represented as H. Now that's the first step in finding the area of the trapezium. Okay, now let's work out the area of the trapezium. I have my H now, so I can work it out. So I'm going to continue here. So we're going to go equals to half. AB is 1,6 plus CD is 2 times this height that you just worked out, which is 24,996. And that leaves you with, now, what does that work out to? I don't have my values here. I will quickly work it out. Give me a minute. So you can do it with me if you have your calculator out. So we go 1.6 plus 2 times 0.5 times 24.996. Okay, so that leaves us with an area of 44,9928, and that is meters squared. So this is the area of the base. Right, now we need to find the volume. So therefore, volume of the pool is the area of the base, as you know, times the height. And we've identified that the base for the shape is the trapezium. And we've got the area of the trapezium, which is 44,9928 times. What is the height? So there's our trapezium here. There's our congruent identical trapezium there, which means it's projected in that direction by that length across. So therefore our height is the 16 meters. And that gives us 719,91 meters cubed. Right, now if I asked you for the volume, that would be your answer. But the question is asking for the pool's capacity. And remember, when you're dealing with capacity is about how much a container can hold. So how much water can this pool hold? And water cannot be represented as meters cubed. We need to convert capacity, please remember, is always represented in terms, in this particular example, we've got to convert meter cubed to liters. Right, so to find the pool's capacity, these examples will be uploaded for you, so you don't have to take them down. Convert meter cubed to liters. Okay. Therefore, how many liters are in 1 meter cubed? There are 1,000 liters. Meter cubed. So to convert that, what would we do? You are going to multiply by 1,000. And that would give you 719,910 liters. Okay, that's the answer. Next question. To find the pool's surface area. Okay, so I'm going to use this piece of paper here to find the pool's surface area. How would you find the pool surface area? So if you think about this, let's look at this here. The inside, they want to paint the inside of the pool, so you've got that wall, those two identical walls, you've got those two identical walls, and then you've got the inside. So that would be the sum of, so the total area would be, so the surface area would be the sum of the two, let's call them the trapezium walls, plus the bottom floor, the base there, plus the two rectangular walls, plus two rectangular walls. And if you look at the measurements there, so the area of the trapezium walls we've already worked out here. So instead of writing all of that again, we're just going to go 2 times that. That's area of one wall, so the area of the two walls would be 2 times that answer there. 2, 44, 9928 plus the area of the bottom floor, that's a rectangle, so it'll be 16 by 25. So that'll be 16 by 25 plus this rectangle here, that is 2 by 16. There's actually two different rectangle walls, please be careful. So they are not the same measurement. The first rectangle wall is 16 by 2. Plus the second rectangle wall is this one. So if you look here, this one is the 16 by 2 and this one is 1,6 by 16. By 16. So that would give you the surface area of this pool, or the inside of the pool, and that would be 547,59 meters squared. Okay, grade 10s. I'm going to leave you with these two examples, and we'll continue in the next lesson with a few more examples. Please complete the work on Google Classroom, and we'll see you tomorrow. Bye-bye.